Yep. Yeah, you could start.
Okay. So hello everyone. Um, I'm just quickly going to open my video for a minute so that you can see who I am. And yeah, my name is Kritika. I am a sixth year student from the UG 2K15 batch. And my research work is on differential privacy. And so, yeah, I thought it would be a good idea to talk about this. So thank you for your time. Thank you for coming. And thank you, Anirudh, for helping me do this. So in this in this talk, we're just going to start with, we're just going to discuss a couple things. One, the first thing would be why we even need computational privacy, which might be obvious, but I'm still going to talk about it. Then something that's known as plausible deniability using a mechanism known as randomized response. Then I will be talking about differential privacy, and finally, its applications. So, okay, so first we start with the need for computational privacy, and we look at some motivating examples that have happened in real life. So in 2006, starting 2006, Netflix started releasing this challenge every year, which had a huge prize where basically they would give you this entire data set of maybe they would tell you, okay, this person enjoyed watching this movie and did not enjoy watching this movie, and so on, or these are all the movies that this person has watched. And the challenge was to come up with a good collaborative filtering algorithm to be able to predict user ratings for each movie or each TV show that you have on Netflix. So the way they kind of wanted to do this in a crowdsourced manner, they released it publicly. They released the user data publicly. And all they did to say that the data was private was that they removed the names and any identifiers of people from that data set. So a year later, when the second round of this Netflix challenge happened, a few researchers from UT Austin, they did something interesting. They took the IMDb public data set and the Netflix anonymous data set, and they basically correlated and combined them to be, and at the end of it, they were able to figure out with high probability that, okay, in the original Netflix data set, I know who each person is for a huge number of records. So this was a very clear and evident breach of privacy, even when the so-called Netflix dataset was anonymous and they claimed it was private, which they were required to do by regulations. So this was pretty much contemporary to the time of when the field of differential privacy began. So differential privacy is extremely recent. It was basically invented in 2006. So kind of prior to that, there have been multiple methods that have been used to enforce privacy, or to make sure that people are getting the privacy they need, as well as they get to use the tools that give them value. And some of those methods are distributed computation, where you don't have one single source of all the data; encrypted computation, which is a very broad field; and other techniques, more privacy specific techniques, such as data swapping, where basically, I would swap some of the details of the people in the data set; and k anonymity, which basically says that you and a group of other k-1 people will not be, like, you will not be able to distinguish between these k people in the data set. And anonymization, as we saw in the Netflix challenge data set, and rule hiding, so hiding some key pieces of rules or inferences that were that were learned in the process of some data analysis. But a lot of work, a lot of research work has generally gone into showing that this is not enough to give people a strong guarantee that their data is private. So um, yeah. So basically, the goal is to have a privacy preserving method of performing data analysis. And one another general motivating example is looking at the Census Bureau of any country. So they collect so much of our data, and the whole purpose of doing that is to help us and make better decisions within the country for the people. But such things can be prone to major privacy breaches. So if you think of what the adversary can do when it comes across some sort of anonymous data, the first thing it can do is, okay, say the adversary is looking at a cancer data set, a data set of people who have tested positively for cancer. It will be the first thing that it would try to do is, okay, maybe it's trying to figure out who is in the data set. So that attack is known as a membership inference attack, whether this person, Alice, is in the data set or not. The second thing is what is known as a data reconstruction attack. So now you can think of something like a deep learning model, maybe, where basically you've learned maybe a CNN based model from a lot of images, and you don't want anybody to see the images, but you want people to use that machine learning model. So what it's possible that the neural network is memorizing the data which it's learning from. So the adversary can reconstruct the original input data from the model. So that's another kind of attack. And the third kind of attack is the linkage attack, which we saw in the case of Netflix and IMDb, where basically you link your data to external sources of data to infer more about it or to de-anonymize it. So the intuition that is behind differential privacy is that if we introduce uncertainty or randomness in the process, then that would also introduce uncertainty for the attacker or the adversary. And uh, the first step to kind of tackle this problem is to start with a simple mathematical guarantee on the entire process or the algorithm. And and we want to be able to quantify how much privacy we have and how much privacy we're losing out on. So yeah, so one last example to kind of go a little deeper into the motivation behind differential privacy. So say we're trying to maybe the hypothesis we're showing is that smoking causes cancer. Now we need to prove this hypothesis somehow, which means that we need to collect data from people who are smokers and non-smokers and try to see how what is the probability of getting cancer in them, or how many of them actually do have cancer. So there are two levels of harm that people uh, can can face in this situation. The first level of harm is by the act of smoking itself. So if through some form of learning or some form of data analysis, we are able to say with high certainty that yes, smoking causes cancer, then this this thing that we've learned is a good thing, and that can help to eradicate harm one, or the first harm, that uh, smoking is going to damage your health. But there's a second kind of harm in this process, where basically if a smoker X has participated in such a data set, and if any insurance company gets to know that okay, this smoker is part of the data set, then it's possible that they might not give him the health insurance that he's looking for, because they know that he might be needing a lot of money at some point for the treatment, or they might give him a much higher insurance fee. So that's the second kind of auxiliary harm that comes out of just getting to know whether a person is in the data set or not. And that is kind of the way we look at membership inference attacks, and why we need to come up with a method to make sure that those attacks don't happen. So yeah, just a very quick pause. Does anybody have any questions up until now?
Excuse me, ma'am.
Yeah.
Um, you like I didn't quite understand what we meant by putting upper bounds on privacy laws. I don't think I understood.
Yeah. Yeah. Okay. We'll get to that. Don't worry about that. Any other questions? Okay. I'm going to continue. So this is the second part, where this is where we're going to talk about plausible deniability and the randomized response mechanism. So, I'm asking you all a question: that did you vote for the BJP? So, ideally, as a nation, we would want to know. So, for example, these pre polls happen before the election, where various organizations try to get an idea of what fraction of the votes are going to BJP, what fraction of the votes are going to Congress or any other party. So, if you want to do some sort of data analysis like that, where you're trying to get an accurate representation of the entire population, but at the same time, you every person has that right to privacy, that like if I am casting a vote, I have the right to privacy. I don't need to tell anybody whether I voted for the BJP or the Congress or whichever party. So how do you come up with a mechanism to survey people, or to query people in such a way that people are free to speak their truth openly without being held responsible for their answer. So that is what is known as plausible deniability, where basically you are helping the cause of the survey, but at the same time, nobody can pinpoint at you and say that, yeah, I know that you have casted a vote for the BJP. So in this example, uh, say there's one person, and say it's Anuruddh, and I'm asking Anuruddh if you voted for the BJP. And now this is how I expect him to answer it. So I'd ask him to pick a random integer x, and if x is odd, then he'd be answering truthfully if he's voted for the BJP or not. And if x is even, I'd ask him to pick another random number y, and when that random integer y is picked, if it's odd, I'd ask him to answer yes. And if it's even, I'd ask him to answer no. So when Anirudh finally says yes or no, I will never know if that's his truthful answer, or if it's because of this second path that you see of picking two random numbers. So this is kind of the starting point, that bringing uncertainty into the process of data collection is going to help with making the adversary's job much harder. So yeah, now we'll start looking into differential privacy. So as it is mentioned in the slide, it is a system for publicly sharing information about a data set, um, in such a manner that no single person's contributions are exposed, but at the same time, we get an idea of the bigger picture. And the way we do this is we add random noise to the process of data inference. And yeah, the good part about differential privacy is that it doesn't require us to specifically model what the adversary is going to look like, because it is the worst case guarantee. And the other thing that is that we are able to mathematically or numerically quantify how much privacy we're getting and how much we're losing. And the other thing is that when we have the amount of privacy that we have, we can compose this privacy loss over multiple queries being asked to the same database. And another key thing which is often not brought up is that differential privacy is a subfield of cryptography. And you can see that because it uses random distributions and things like that. So but I think the advantage that it has over cryptographic methods is that it's fast, and it does not have to go to this encrypted space where things could be much slower or more challenging. And so, yeah, it has certain advantages over cryptography. And yeah, we're going to move on. So consider the simple example of the number of visitors visiting a restaurant on say a Monday. So on this Monday, the number of visitors that visited the restaurant at 3 p.m. There were 10, and so on. So this is like a histogram of the number of visitors at different times of the day. So um, what happens if suddenly a person visits at 1 a.m. on that day? So so if I were to try to figure out whether say visited, if I know if I'm trying to figure out whether Fizza visited this restaurant at 7 p.m., it's a lot harder for me because there are 14 other people who visited at the same time at 7 p.m. And it gets harder. But if I know that only one person visited this restaurant at 1 a.m. and by some way I know that okay, maybe Fizza was awake at 1 a.m., then that means that it's Fizza. So just that small difference in this statistic, which can help me narrow down that okay, this specific person that I'm targeting has visited, and suddenly I have more information about this person. So that is a privacy breach for Fizza. So what differential privacy is going to be doing is when somebody asks for this histogram, like I just want the histogram of how many visitors there were on Monday, then instead of actually giving the exact numbers, we're going to add some very little random noise to it, which could come from distributions like the Laplacian or the Gaussian distribution. And it would look something like this. So every time somebody asks me, how many visitors did you have in each hour of the day on Monday? I'm going to kind of randomize it a bit. So what's happening is that um, no adversary will be able to say that, okay, exactly at 1 a.m., I know that Fizza or any other person visited this restaurant. But at the same time, the bigger picture, like the shape of the histogram, the general the distribution of the population, that is still being preserved. So normally in any sort of data and analysis pipeline, what's going to happen is you start with some input data, and that comes from people. And the the thing that you do is you pass it through a query function. And that function could be something as simple as finding the minimum value in the data set, or it could be something as complicated as a neural network. And then what you get is the output of this query function. So what happens if hypothetically I look at a data set D, and I look at a data set D prime, which has all the people in D except one person, and that could be any one person. So such data sets where those two data sets differ in exactly one data point, those are known as neighboring or adjacent data sets. So here, what you see that normally when you would compute the query on these two neighboring data sets, the outputs that you get will be different. So for example, the number of visitors with and without Fizza would be different. So this is the way membership inference attacks can happen, where you make very small, you try to observe the very small changes in the input by actually observing the small changes in the output. So what differential privacy is doing is that it's modifying the query function in a sense, and it's making it a noisy query function where basically at some stage within the entire process, you're going to be adding noise. And what's going to happen is that for any two adjacent data sets, the final output that you get is basically the same. And by basically the same, I mean that every time I'm going to ask for f of d, every time I'm going to ask for f of d, I'm going to get a different value because this is a random function at this point. So what you will see is that the probability distributions of this and this are going to be the same. And yeah, so more formally, let's get to defining differential privacy. So here, the definition is stated as a randomized algorithm M gives us an epsilon differential privacy guarantee if for all pairs of datasets D and D prime differing in one person and all possible outputs S, the probability of M of D being equal to S and the probability of M of D prime being equal to S, this ratio is upper bounded by e to the power epsilon. And normally, epsilon is a very small positive value. So this ratio of probabilities, or you can say the another way to look at it is the divergence between these two probability distributions is upper bounded by e to the power epsilon. So for the rest of the presentation, you'll be seeing this epsilon term come up again and again. And this epsilon is what is known as your privacy budget. And it it is an indication of how much privacy you are achieving in the process of randomization. So if my epsilon value is really small, let us assume that epsilon value is 0, then in that case, these two distributions, probability distributions, have no divergence at all because they are upper bounded by 1. Their ratio is upper bounded by 1, which means that's perfect privacy. So the smaller the epsilon, the higher the privacy that you get. And with large values of epsilon, maybe in the range of 5 to 10, you get very weak privacy guarantees. So this is like the key contribution that you are able to quantify the privacy that you're losing. And as you can see, it's a symmetric formulation. So I could have replaced D and D prime with each other, which means that this privacy guarantee holds if I remove one person from the data set and if if I add one person to the data set. It's just a difference of one. So yeah, and uh, so this one way to interpret it or think about it is that if a bad event is very unlikely in if I'm not in the data set Y, the data set Y being D prime here, which means a bad event like maybe not the investment, sorry, the insurance people being able to tell if I'm a smoker or not. That bad event is very unlikely if I'm not in the data set Y or in D prime, then it's also very unlikely when I am in the data set. So what that gives me is the freedom to freely participate in data sets and to freely contribute to um, data analytics and research and good applications that help people. So if I have such a guarantee, I wouldn't think twice about contributing to a data set if I'm a smoker, if I have sensitive information. So this overall helps with the goal of real or accurate data analysis. Okay, so let's go back to the randomized response mechanism that we looked at, that with 50% probability, any BJP voter will say the truth, and the truth is that the truth is yes. And with 50% probability, the BJP voter will give a random answer. And within that 50%, half the times he'd say yes, and the other half the times he'd say no. So overall, the BJP voter would say yes with a 75% chance. And the number of times it would say no, that probability would be 0.25. Similarly, you can see that people who haven't voted for BJP, they would say yes 25% of the times, and they would say no 75% of the times. So how do we formulate this in terms of differential privacy? So we have these probability values. And here, what do we have to look at? We have to look at the probability of BJP voters saying yes and the probability of non-BJP voters saying yes. So this ratio of probability of BJP voters saying yes and non-BJP voters saying yes is 0.75 by 0.25, which is 3, which means that this is upper bounded by e to the power epsilon, which is 3, which implies that here in this case of 50% deniability at all times, you are going to get a privacy budget of which is natural log of 3, which turns out to be around 1.1. So normally when you see differential privacy being applied in a lot of applications in deep learning and SQL like databases, you will see that people usually start with an epsilon of 1.1, and that basically means that I want 50%. I want the adversary to only be able to have like a 50% better guess than before. So here, uh, this is the interpretation that if an adversary thinks that the chances of me being a BJP voter is 50%, then the adversary's chances can only increase up to 75%. It cannot go beyond that for sure. So this is what the um, kind of adversary belief looks like for an epsilon equals 1.1. So here you can see in this graph that at 0.5, this is the minimum that the belief can go to, which is 0.25, and the maximum that the belief can go to is 0.75. So if you were to think about this, the smaller the epsilon, the better the privacy guarantee you have, right? So here, as you see, that for a very small value of epsilon, this window of uh, basically how much the belief of the adversary can change is really small. Whereas for a high epsilon, something like 6.5 or 7, it's all the way from here up to here. So for example, if I had an epsilon of 7, then even if I had, even if the adversary initially thought that the probability with which I'm a BJP voter is 0.1, that could directly take the adversary to almost 100% probability, saying that, yeah, she's definitely a BJP voter. So this is how you start to understand what the privacy budget is and how you can apply it based on the use case. And the important thing to remember is that it is still a controllable parameter. So some use cases, it maybe the data that you maybe the data set that you have, the person you're giving it to, maybe you trust that person a lot, so you don't need to use a very small epsilon. But cases where there is close to no trust involved, then you will have to use a very small epsilon to get a really high privacy guarantee. So yeah, important thing is to know how much trust is already in the system, and yeah, use that trust as much as you can, because as we will see slightly later, increase in privacy is going to cost you accuracy, or any form of utility that you can measure in data analysis. So how do we go about doing something which is a more of a general mechanism in differential privacy, as opposed to kind of the specific randomized response that we saw? Uh, we know that we have to add random noise. So, okay, question 1, what's the noise distribution going to look like? From where am I going to fetch my samples? So there are a few distributions of choice, such as Gaussian and Laplacian, and a couple more in the exponential category, which are being used. The second point is, okay, now that I know which distribution I'm going to fetch my noise from, what are the values of that, like in what range does that noise lie? And that is determined by two things. There's privacy budget and there's something called query sensitivity. So we've looked into privacy budget quite a lot by now. And once again, to reiterate that privacy strength is inversely proportional to the value of epsilon. And the next thing is query sensitivity. So this is where you start looking into the query itself. You try to understand that this query that we're performing on our data, how much of the query output changes when we remove or add 1% to the input data set. So For example, if our query was just a count of the number of people in the data set, then the query's output value would change by 1 if we added or removed someone. But if say the query was say the data set also had heights and weights of all the people, then if the query was say sum of heights of all the people in the data set, then by adding or removing one person from that data set, the query output could change by something like 6 feet or 6.6 feet 3 inches or something for really tall people. So that's what the sensitivity of the query means, that how much is it going to affect the output when the input changes just by one person. And that here you can see is being measured by the L1 norm, max L1 norm value that you can get for any two neighboring data sets, D1 and D2. So, so for example, let's look at the Laplacian mechanism. It's one of the simplest mechanisms in differential privacy. So we know that we need to sample noise from this distribution, and the distribution is analytically defined in this manner, where the mean, mu, and b parameters are helping you basically define the shape and the size of this Laplacian mechanism. So this is where the privacy budget and the sensitivity come into place. We start with a mean of 0, usually for most of these differential privacy noise mechanisms. And this B parameter is directly proportional to the query sensitivity, and it's inversely proportional to the privacy budget as as our mind would say so. So this is basically what's going to be coming in here in the equation. And then you'll have kind of this Laplacian mechanism with zero mean and certain variance defined by this parameter. And so now, like, let's try to understand why this Laplacian mechanism is giving us the differential privacy guarantee. So let's assume a simple, don't take the randomized response thing into account here. I'm just still using the BJP example. So let's say that I have a data set, and we know that that data set without, so let me pick up another person in the crowd here who I know. Let me see. Okay, I know Shashwat. So let's say that Shashwat was a BJP voter. But right now, he's the target. So let's look at the number of votes in the data set without Shashwat. And that is, say, 1,000 people have voted for BJP. So basically, now what we have to do is we're going to be adding noise to this number, 1,000, right? When we return the query result for somebody asking how many votes, how many BJP votes are there in the data set. So now there's an adversary who just wants to know whether Shashwat has voted for BJP or not. That's it. That's all the adversary wants to know. So it's possible that maybe the adversary gets to know that, okay, at this point, I know that Shashwat has just voted. So right after that, the adversary is going to query the database and ask how many votes have been there for BJP. So since our query engine or query machine is smart, and so what it gives out as the result is 1,003. So now, even though only one more vote has been cast, which is Shashwat's vote, it's showing that there are 3 more people who have voted for BJP, which of course doesn't make sense, but that's the point, because we're adding noise to preserve the privacy of Shashwat and anybody else. So if you were to think like a smart adversary, you would look at these two possible situations of what the noise distribution would look like. So the blue curve here is suggesting that this is the true BJP vote count when with Shashwat in it, the true vote count is 1,001. And the orange curve is suggesting that with Shashwat in it, the true BJP vote count is 1,002. So Of course, the blue curve is more likely than the orange curve because we're only measuring it with and without one person, which is Shashwat. So how much more likely is the blue curve compared to the orange curve? That probability is bound by e to the power epsilon. And that is where, like, you can see the significance of that mathematical guarantee holding with every single query that you ask to the database. It may seem like a simple operation or something, but it's extremely valuable in practice. Differential privacy gives us this power to compose the guarantee over multiple queries. So here, as you can see, if we have one randomized algorithm M1 with an epsilon 1 budget and another algorithm M2 with an epsilon 2 budget, of course, on the same data set, then publishing the result of both is going to cost us a budget of epsilon 1 plus epsilon 2. And as we know, the higher the budget, the lower the privacy guarantee. So this would um, gracefully and linearly decrease your privacy guarantee with composition. So this is what is known as basic composition in differential privacy. And a lot of research work goes into improving this bound. So people have found sublinear compositions and in the order of log space, and it there's a lot of active theoretical research going on in purely query composition. One direction that people have taken here is to start looking at different divergence measures itself. So in the beginning, I spoke about how the differential privacy definition is like looking at the divergence of those two probability distributions being bounded by e to the power epsilon. So there's something known as Renier differential privacy, which uses a more general version of Renier divergence as its base, and that is extremely interesting. So um, yeah, so the properties that we see is just to kind of summarize is that we don't need any sort of adversary modeling because this is the worst case situation that we're trying to give privacy to. And the privacy loss is quantifiable. And that basically shows what is the greatest possible information gain the adversary can get in any situation. And this property hasn't come up till now, but it's future proof. So what that means is once I have released a query, which is differentially private, query result, which is differentially private, or once I have even released the entire data set, which is differentially private, any post processing you do on top of that is not going to make things worse. It's not going to end up giving you a worse guarantee than before. So yeah, another thing is something called group privacy, where basically instead of looking at the privacy when one person is in the data set versus when that person is not, you look at what happens when a group of people are in the data set and when they're not. So very neatly, what happens is just multiplies to k times epsilon for a group size k. And yeah, we already spoke about how differential privacy undergoes composition very neatly. And the thing that had come up when we were talking about cryptography is that it's very easily programmable. And I mean, it's quite simple. You just have to kind of add these random noise distributions and in the right way, calculating the right privacy budget, things like that. And so yeah, you're able to get a really strong mathematical privacy analysis from very simple building blocks, which is a great plus point when you are working with people who are not mathematicians or privacy people. Maybe they're just generally data scientists or engineers or even people from different fields. So that is a great advantage. Then some of the applications, this is like the final section of the talk. One of the huge areas of applications is in healthcare. So how can we use more data analytics and AI in healthcare to be able to, do some really good medical work, really help people in diagnosis or maybe even genomic related stuff, but the biggest problem right now is that we don't have access to the data sets. So that's the bottleneck. We don't get access to hospital data as easily as we have access to handwritten image data sets. So the way we do that is by showing these hospitals and huge organizations that we have a way to um, ensure mathematical privacy for every person. And yeah, another thing that you will see is already differential privacy is heavily used in Google and Apple. I'm sure it's used in other places too, but these are the two cases that I know of very well. And so, for example, how do you get an idea of usage statistics over many people in Google Chrome? So there's something called Rapport, which is a unique differential privacy framework that they use to do that. In recent context, we have seen that contact tracing apps do not really require our location data or our personal data or anything. They just need access to Bluetooth. And through this network of Bluetooth connections and some encrypted messages or ciphers, they are able to effectively, perform contact tracing. But still, despite that, countries around the world have been using contact tracing apps to get to basically take a lot more data from people. And yeah, that's not okay while there are no proper privacy standards. But if there are, then it's great. There's a lot that can be done with our personal data, which can help everyone. And okay, so the next point is probably shouldn't go too deep into that, but federated learning is like distributed machine learning where you might have multiple models and then you in different places and you bring them together. And so in such distributed settings as well, your data is going to different servers, different places. So to be able to trust such a system to work for you and not against you, differential privacy becomes really important. We had looked at Census Bureau. More generally, IoT, Internet of Things, you'll find that a lot of these objects that we have at home are really, like, for example, people's suspicions of things like Alexa listening to our private conversations and things like that. There's a very important kind of motivation there for privacy, where we want to use these really good IoT applications and devices, but at the same time, we don't want them to be invading into our personal lives. And yeah, so more specifically, like more at a data analytics level or a machine learning level, you will see that a lot of neural network training or machine learning in general faces this problem of overfitting and memorizing the data rather than actually generalizing and finding some really good hypotheses. So we can combat that specific aspect of how can we avoid neural networks from memorizing the data by actually introducing this another good thing where you're adding privacy to your neural network models. And my research is in a subfield of that. My research is in the field of looking at differential privacy in deep reinforcement learning. So there's more interesting sort of interpretation of how what it means for someone's privacy to get invaded in a reinforcement learning setting. So those are the applications. Here are the references. I will be happy to share the slides after so that you can look into the references. And that's it. That's the talk.
Yeah, thank you very much. That was really nice. Uh, yeah, before we go on, yeah, so there are a few questions in the chat. Like those who ask, can you ask your questions again?
Yeah.
Like if you still are confused about that, you can unmute and ask.
Yeah.
Excuse me.
Hi, who's this?
Hello, this is Vivek. I'm a UG1 student. Um,
Okay, hi.
um, so my question, I didn't quite understand a lot, but one thing I understood the example of the polling station well. So, but uh, isn't differential privacy going to always skew the data? Like, so if we were to skew the data too much, wouldn't it become like not? Wouldn't it not be useful to predict things anymore? Um,
Okay. So great question. Um, what I would uh, ask you to think about is how do you introduce skew in a data set? So to kind of look at skew, you would first look at the underlying distribution of the data. And when you look at these noise distributions that we're using, they are centered around the a zero mean. So in a very symmetric fashion, they are going to be adding very little noise compared to the actual data. So what it does is that, of course, it makes the data less accurate in some sense, or it does modify the probability distribution in some sense, but if you look at it in the the law of large numbers sort of sense, it's not going to count. It's just going to normalize everything. So it's not going to introduce any sort of skew in the data set.
hmm, okay, thank you.
Yeah. Other questions? Yeah, I think most of the questions in the chat were also
Okay.
the same thing.
Yeah.
Uh, so yeah, if there's nothing else, I'll be stopping the recording now. Yeah, thank you very much for the talk.